Welcome back, students. We are now going to start work on the CPU. We are going to start by discussing the central processing unit. So getting started, recall that the CPU, or the central processing unit, acts as the brains of the computer. It carries out the instructions of a computer program by performing the basic arithmetic, logical, control, and input-output operations specified by the instructions. More specifically, the CPU fetches program instructions from RAM, so your input, interprets and processes it, which is the execution phase, and then sends that back to the computer results so that the relevant components can carry out the instructions. In this lesson, we're going to delve a little bit more into what makes a CPU and how it works. So let's start off first by asking, what is a CPU made of? Well, a CPU is a complex integrated circuit made of silicon, which has billions of microscopic transistors mounted onto it. The CPU is typically enclosed by a metallic heat spreader, which allows for better heat dissipation. Now, granted, it's just dissipation, it doesn't necessarily cool it. That's why we also have to, like in larger units, you need to have like a fan and stuff like that over top of the CPU. Now, most modern CPUs are microprocessors, meaning that they are contained on a single integrated circuit chip. Some computers also employ a multi-core processor, which is a single chip containing two or more CPUs known as cores. So let's discuss the physical composition. So right up here, you'll see I have an example of a CPU on two sides. So you have the circuit side, and then you also have the plate. So these are the two faces, the smooth metallic side, that is what's known as the heat spreader, whereas the bottom, which is your active circuits there, you can see it's covered with gold pins. Additionally, these little interactive pieces here is what also helps connect in. So these pins here connect in with your motherboard, and then you also will have these right here, which will also connect in as well. So all that's part of the interface there with the motherboard. And this is just the heat spreader. The form, design, and implementation of CPUs has changed over time, but fundamental operation remains almost unchanged. Almost all CPUs today follow what's known as the von Neumann model, so they're all kind of similar in a lot of their function. Now, the principal components of a CPU include the arithmetic logical unit, or ALU, which performs arithmetic and logic operations. You have the processor registers, which supplies operands to the ALU and store the results of the ALU operations. The control unit that orchestrates the fetching from memory and execution of instructions by directing the coordinated operations of the ALU registers and other components. Now, those of you that may have taken computers and logic might recognize a couple of these terms from when we talked about the LC3. Because what the LC3 was pretty much a little tiny computer, and so we were working a lot with the stuff that would be handled by your CPU, because that's a central processing unit. And so we talked about things like the ALU and processor registers and control units. But before we get into any more of that kind of talk, let's first discuss clock speed. Clock speed refers to the frequency at which the chip is running. So a CPU, that processes one instruction per second will have a clock speed of 1 hertz. Based on this calculation, when you hear something like a 3.9 gigahertz CPU, that means it's able to process 3.9 billion instructions per second. Remember, giga is a billion. So that's 3.9 billion instructions in a second. So if you have, let's say, a 3.6 gigahertz processor, that means it's processing 3.6 billion instructions per second. And that's a lot of information. Now, the general rule is higher clock speeds equate to a faster CPU. Now, it's not exactly just the clock speeds. There's other things that factor into it, obviously, but the general rule is you want a higher clock speed. The other thing, though, is cores. Cores also make a difference. If you had, for example, a 3.6 dual-core CPU and a 3.6 core, at 3.6, let's say, quad-core, obviously the quad-core is going to be handled more. So a single-core CPU has to process instructions one by one in a sequence. Like, it doesn't matter if it's dual-core, single-core, quad-core, whatever. A single core processes one set of instructions one by one in sequence. So dual core will be able to handle these now two instructions simultaneously, because now you have two cores to be able to process information. Now, just by upping it to the dual core, this vastly improves multitasking capabilities, and it allows it to run multi-threaded applications much faster. And obviously, if you go to quad core, it's even faster, or if you had a 6-core or an 8-core. Now, multi-threaded applications are programs written to take advantage of 2 or more CPU cores at the same time. Many modern software are able to make use of 2 cores, while demanding games can use even up to 4 cores. Certain CPU-intensive processes, such as data editing and virtualization, can utilize 8 cores or more at the same time. Now, physical cores versus threads. All right, because I've talked about physical cores, but I also kind of mentioned some threading stuff. So let's just discuss that. Now, both Intel and AMD support physical cores and hyper-threading technology. Now, threading, how it really kind of works is that it tricks your operating system into thinking that there are 2 CPUs, or there's more than just one. So there's some fancy software stuff I'm not going to really get into how that works, but just very much so that what the threading does, it kind of, if let's say you had a 4-core processor, to the computer, it's like it has an 8-core processor. That being said, while it does increase parallel speeds, it's nowhere near as fast as having another physical core. So remember, a physical core will always trump a hyper-threaded core, because a hyper-threaded core, remember, it's split into 2, and it's kind of simulated that there's another core. It's not like having that physical core, because even though it's hyper-threaded, this is because the machine can still only process one instruction at a time. So the computer is like, hey, I can run 2 things, which is true, but physically, it's still only going through that one channel. Now, let's talk about the fundamental operation of CPUs. The fundamental operation of most CPUs, regardless of physical form, is that they take is to execute, there we go, a sequence of stored instructions that is called a program. The instructions to be executed are then kept in the computer memory, and nearly all CPUs will follow the cycle of fetch, decode, and execute in their operation, which is collectively known as the instruction cycle. And again, computers and logic, if you took this class, this is going to seem a little familiar for you. So let's talk about the fetch phase. The first step, fetch, involves receiving an instruction, which is represented either by a number or a sequence of numbers from the program memory. The instruction's location, or the address in program memory, is determined by a program counter, or in this case called a PC, not a personal computer, but program counter, which stores a number that identifies the address of the next instruction to be fetched. After an instruction is fetched, the program counter is incremented by the length of the instruction so that it will contain the address of the next instruction. Often the instruction to be fetched must be retrieved from relatively slow memory, such as, like, for example, your hard drive, which causes the CPU to kind of stall out a little bit while waiting for the instruction to be returned. Because while the CPU is going lightning fast, the hard drive doesn't move quite as fast. Now, this issue is largely addressed in modern processors by using things like caches and pipeline architectures in order to help speed up, data retrieval. All right, next phase, decode. The instruction that the CPU fetches from memory determines what the CPU is doing. So the fetch phase says, hey, here's the instruction, now we're going to do something with it. In the decode step, the instruction is converted into signals that control other parts of the CPU. The way in which instruction is interpreted is defined by the CPU's instruction set architecture, or ISA. Often, one group of bits within the instruction, called the opcode, indicates which operation is to be performed, while the remaining fields usually provide supplemental information required for the operation, such as the operands. Those operands may be specified as a constant value, called an immediate value, or the location of value that may be a processor register or memory address as determined by some addressing mode. All right, the last phase is execute. After the fetch and decode steps, the execute step is performed. Depending on your CPU architecture, this may consist of either a single action or a sequence of actions. Now, during each action, various parts of the CPU are electronically connected so they can perform all or part of the desired operation. Then the action is completed, typically in response to a clock pulse. Very often, the results are written to an internal CPU register for quick access by subsequent instructions. In other cases, results may be written to slower but less expensive and higher capacity main memory. Post-instruction cycle. After the execution of an instruction, the entire process repeats. So it goes all the way back to the fetch phase, and then decode, execute, repeat. With the next instruction cycle normally fetching the next in-sequence instruction because of the incremented value of the program counter. Program counter says, okay, did this, now let's go to the next one, and then the next one. Those of you that remember this from the LC3, remember you could watch the program counter increment as you went through each line of memory. Now, if the jump instruction was executed, the program counter will be modified to contain the address of the instruction that was jumped to, and program execution continues normally. In more complex CPUs, though, multiple instructions, rather than just a single one, can be fetched, decoded, and executed simultaneously. And that concludes our notes for today, folks. Until next time.